So we started today a new unit, chapter 3, with this problem. Stephen's a coin collector, and he begins his collection with 25 coins, and every week he's going to be sent 10 new coins in the mail. And my question is, in W weeks, how many coins will he have? And the question is, how do you even begin? And one of you said, you make a table. That's exactly what you do. So if you begin with a table, you can keep track really easily of the weeks and the number of coins that Stephen has as the weeks pass. So you guys made a table and you looked for patterns. So in 0 weeks, Stephen began with 25 coins. The first week he had his original 25 plus 10 more, and that's 35 coins. After 2 weeks he had his original 25 plus 2 groups of 10, which is 20, and 20 and 25 was 45 coins. After 3 weeks he had his original 25 plus 3 groups of 10, which is 55. And in 4 weeks it was 25 plus 4 groups of 10, which is 65. And in 5 weeks, 25 plus 5 groups of 10, which is 75. And you guys were able to talk about that pattern in W weeks. It's the same 25 plus 10 coins a week times the number of weeks. 5 was the number of weeks, and we did 5 times 10. 4 was the number of weeks, and we did 4 times 10. So in W weeks, we do 10 times W. And because this is in the coins column and Y is the coins, we can make this expression into an equation by saying if 25 plus 10W is the number of coins, that equals C, which is the number of coins. And now we have an equation that is another model. Remember, these are mathematical models. We're modeling the situation with words, with a table, and now we have an equation. And from the equation, we can actually do the math. Like I said, for example, the cool thing about the equation is, what if Stephen wanted to know, how long will it take me to get 500 coins? Well, he can take this equation, take out C and put in 500 and work backwards. So if I want to know what is in this blue circle, I subtract 25 from 500. So 10W has to equal 475, and then we divide by 10. And we knew that it was 47.5 weeks, but he gets his coins every week, so it's going to take the 48th week for him to have his 500. At 47 weeks, you guys figured that he had 495 coins, so he didn't have quite enough. So it would take the 48th week. So back to our table. So in your table, it helps you see the pattern to get this expression for the number of coins. And then you graphed it, okay? And our x-axis, which is our domain, is x, are just counting numbers because we just counted as the weeks went by. Actually, it's a set of whole numbers if we begin with 0, but we counted the weeks, the first week, the second week, the third week. Stephen only gets his coins once a week, and because there's no such thing as a 1.5 week of coins, we don't connect the dots. These are actually discrete points that represent Stephen getting those coins that one day a week. He doesn't get coins in between the weeks, so we don't connect the points. We don't have any data that's less than 25, so we can put this little break symbol that tells the reader you skipped from 0 to 25, and then we counted by tens, which makes sense because that matches our data, because he got 10 coins a week. So these are discrete points that we don't connect, and all of our points are in line, which is what collinear means. This is called a linear graph because we are constantly adding 10 each week. And now we use our graph to make a prediction. So I could say, how many weeks will it take Stephen to have 95 coins? So I go up to 95 on my y-axis. I go over to my green dot and down and see that that's 7 weeks. Or I can use it to predict, how many coins will Stephen have in 8 weeks? I go up to my dot, I go over to my y-axis, and I get 105. So the whole purpose of this graph is to see it visually and to use the graph to make predictions. So now we've had 3 models. We've had a table, we have an equation, and we have a graph. All right, it's called a linear equation because all of the points lie on the same line. And this is an example of a situation where we had a constant increase. The increase was 10 more coins a week. So we have a linear equation with an uphill slope because it's constantly getting bigger for the number of coins as time passes. And I said, how will the next situation be different? So this is about a flash flood. The water level in the river was 54 inches above normal. After the rain stopped, the water level dropped 1.5 inches per hour. So we let x be the number of hours since the water began dropping. And I said, how can we model this situation with a table? And you guys figured it out. In 0 hours, it was 54 inches above normal. After 1 hour, it dropped 1.5 inches, so that's subtraction. After 2 hours, it dropped 2 groups of 1.5. After 3 hours, it dropped 3 groups of 1.5. And in X hours, it will drop X groups of 1.5. So we got right away, you guys saw it, Jabari saw it really quickly, that if I want to know how many inches of rain there are, I do 54 minus 1.5 times the number of hours. And this is going to be an example of a continuous graph, because I could figure out, gee, what's the water level after a half hour, or 1.5 hours, or 2 3/4 hours? So it makes sense because measurement is continuous here, and the water level's constantly dropping in that time. So you guys graph that on your graphics calculator. You set your window. So we didn't graph it by hand. We used your graphics calculator. We put in y equals 54 minus 1.5x. And in your graphics calculator, you guys saw that it was 36 hours. So we tested that with the equation to make sure it was correct. And 36 times 1.5 is 54. 54 minus 54 is 0. And when it gets back to 0, it's back to its normal water level. So it totally works. So hours and inches, this is what we did in your calculator. That was the graph you came up with. It's a constant decrease. It goes downhill. And the domains of the situations were very different. We can have any number for x, any real number. So that's why we connected the points in the graph. And then I said, how are the domains of the situations different? Why did it make sense to only use whole number for the coins? And you guys had it. You said because he only gets the coins once a week. He doesn't get the coins in any numbers between 1 and 2 or 2 and 3. So it's really choppy. He gets them on, if he gets them once a week on Saturday, let's say it comes in the mail, then he doesn't get any till the next Saturday. So we didn't have any numbers between 1 and 2 and 3 and 4. But in the water level, it was constantly changing, so we could find any water level for any amount of hours. So that was the set of real numbers. So I said, try one yourself. Sherry bought a new home with a 5-foot deep swimming pool in her yard. The pool started with 1 foot of water, which was 12 inches. Sherry began filling the pool with water, and she noticed that the water level of the pool rose 4 inches every hour. Now we're mixing units of measure here, and I know a lot of you are not familiar with inches, so we looked at the rulers. There are 12 inches in a foot, and so her water level is rising 4 inches out of every 12. So that's 4/12 of a foot, and 4/12 is the same as 1/3 of a foot. So we talked about, gee, if I had 3/3, that would make 1 full foot. So every 3 hours, she's getting 1 foot of water added to the swimming pool. So you guys made a table, and you carried out your table. In 0 hours, it was 1 foot. In 1 hour, it's 1 1/3. In 2 hours, it's 1/3 more than 1 hour, so we added another third. In 3 hours, we added another third, and we get 1 2/3 plus 1/3 is 2 feet of water. In 4 hours, it's 2 1/3, and you carried it all the way down until you guys found that you got to 5 feet. And all of you got 12 hours in your table. So we graphed it and we checked in 12 hours, do we get 5 feet on your graphics calculator? And yes, when we used the trace key, it worked. And if we check the equation with the math, so let me just grab a pen here. So if we just check the equation with the math, if x is 12 hours, remember x is the number of hours, and 12 times 1/3 is 12/3, and 12/3 is 4. So in 12 hours, we had 4 feet of water. Remember, she began with 1 foot of water, and 4 plus 1 is 5. And that's how deep the swimming pool was in the very beginning. So you know that it works. All right, so you did this in your groups, and that's what we came up with. So in ALEKS, you have by Thursday, 1 hour to get done, 5 topics, and you've got this practice problem to do in your book. And you may use your graphics calculators, but make sure you sketch your graph so I can see what you got. Or as Sarahnique said, you could always take a screenshot and you could print it off. It's up to you. That's it. Hope you're feeling better, Diana.